Today we are going to do section 9.6. First, let's look at the book. This is the old page that's already been scanned, so I'm just going to hurry and go to show it to you quickly again, but not take too much time to make it too perfect. That's good enough. Next, page 304 and 305. Let's get a little closer here. Okay, then a bit closer on the top and on the bottom. Well, that should be good enough. Finally, page 306 and 307, the homework page. Okay, a little closer maybe. All right, and then a little closer on the top. And on the bottom. That should be good enough. So let's begin on page 303, the applications of what we have learned so far. The example, first let's reconsider example C on page 300, which is right here. Okay, here's that example where we have a bunch of continuous functions that all converges on a closed interval, and yet it converges into something that was not continuous. Okay, and that raises an interesting point: is when can we guarantee that a bunch of continuous functions that are continuous on a closed interval will end up being will have a result where it converges to something continuous? And that's what we're going to talk about. So please read this introductory paragraph yourself, and then we'll move on to theorem 12. Theorem 12 states that if we have a bunch of functions ukx, they're all continuous on a closed interval from a to b, and then they all add up in an infinite series to become f of x, and in a uniform convergence situation. And if that is the case, then f, the result, will be continuous on the closed interval. Now, to prove that, we're going to let x0 is between a and b, and then we'll find some delta x that's also such that x0 plus delta x is also between a and b. And okay, so far so good. Now, now we're given some epsilon bigger than 0. And given that, then we can use the various definitions. First, being that the partial sums are converging to f, right? Well, at this exact point x0, each point is converging, so therefore we can find something such that some integer m such that this relationship is going to be less than epsilon over 3. That's at a single point, okay, and where the partial sum is going to be will be within epsilon over 3. The second part is at the next point, x0 plus delta x, the delta x that we made up. The delta x isn't necessarily small, okay? It just has to be within b. That is, x0 plus delta x will be within a and b. That's all that matters. So as long as that's true, so delta x, which might not be small, this relationship, that is the original relationship here, replaced with this, will still be within epsilon over 3. And this will be true even if you change delta x to some other value that as long as satisfied is within range between a and b. That is x0 plus delta x. As long as it's within a and b, then this inequality also holds. Is going to be less than epsilon over 3 if you choose m to be big enough. The reason for that is because the convergence is uniform. And because uniform convergence does not care where your partial sum is. Okay, whichever x it is, it will be within the given epsilon once you pick the the m to be big enough. So both conditions are now satisfied due to the uniform convergence, and that's where we use the uniform convergence the strongest. Well, of course, as a side note, these uniform convergence means that these inequalities that we just mentioned will hold if m is replaced by anything that's bigger than m. But we don't care about that right now. Okay, and we just stand the fact that SMX, the partial sum, is going to satisfy these conditions. And then next, because next we consider the partial sum as m of x, being that it is continuous. Okay, it is a finite sum of continuous functions, therefore it's continuous. Then there exists a delta such that if we pick delta, the original delta x to be less than delta, then so if this, now we're going to restrict this thing. Okay, so if delta x is less than delta, then this relationship will hold. But this is only because SMX at the partial sum is continuous function, so this is possible. So at this point, we're restricting delta x to be less than delta, and to make this possible. So now we have three inequalities, and what that means is once you combine the three inequalities, then we will get the last inequality, which is what we want. Now to combine these three inequalities, I've drawn a graph here, which I think the book should have drawn. But anyway, what happens is the first inequality is this one, okay, the green one, which is f of x0 minus sm of x0, the green part, okay, that's less than epsilon over 3. The next one is the purple one, that is f of x0 plus delta x, which is over here, and minus sm of x0 plus delta x is also less than epsilon over 3, so this part distance. And the last one is that is the red one, where Sm, this is using Sm is being continuous, whereas m of x0 minus Sm of x0 plus delta x will be less than epsilon over 3. But this has a more restrictive condition where delta x has to be less than delta. Now if that means the very last point, okay, that is the last distance, which is f of x0 minus f of x0 plus delta x, this is going to be less than this plus that, okay, that's due to the triangular inequality. And so, because this minus this is this minus that, and then well, anyway, you add all these three inequalities up, then that will be equal to this one, okay, because f of x is minus sm x0, and then plus xm x0 minus sm x0 plus delta x, and then there's a plus, and then the minus. Anyway, the point is, well, you can switch these two around. The point is, you end up with just this, okay, applying the triangular inequality. And then at the other side, the three epsilons added up will be less than epsilon. That is the distance, the shortest distance between 2 points is a straight line. So all this stuff is a roundabout way of getting there from geometry's point of view. Then that's why the distance is going to be less than. So we have established that. So we have established this situation where it's less than epsilon if delta x is less than delta, and that of course proves that this thing is continuous, okay, within the little range from A to B. Now and remember that this rule applies because the uniform continuity was being used. That where this inequality 1, this one right here is true for all x, delta x. Okay, this part is important. Otherwise, this proof wouldn't be working quite as well as it should. And it works for all delta x such that delta x is less than delta. And of course, it is within range because we don't care about being out of range. So that is and that is how this theorem is proved somewhat nicely. Okay, so basically it just used the triangular inequality and lean heavily on the fact that it is uniform convergent. Now to see this one, then let's turn to the next page, to 304, where we consider, but we're going to look at example A back into page 299. We have, well, back in 299, we had an example of uniform convergence of a sequence of continuous stuff, as that is, if it converges in from minus a to a as long as a is less than 1, okay? Then this sum will converge, being that each x is less than 1, so it converges uniformly to this thing, as we have seen there in some kind of a proof previously. That is example 1. Next, continuing on page 302, we also consider let's see, what am I doing? No, not 302. I said that wrong. 304. And then, and we'll also consider that example B in the same section, which is on page, the same page, 299. Now, example B is a counter example where the function converges uniformly, converges, but not uniformly. In other words, the condition of what the Theorem 12 is not necessary. Okay, it's sufficient but not necessary. There is a way that a series of stuff can converge to a continuous function, even if the series itself is not uniformly convergent. Okay, so that is that. Next, let's consider subsection 6.2 on page 304. Now, if we have a convergent series, can we integrate term by term of the series? That is, if f of x is equal to a convergent sum, can we simply, does the integral of f equal to the sum of the integral of what's inside? Now, that doesn't always work. Okay, and we can show it by use of example B on page 299. That's this thing down here. Okay, on page 299, the example B, which have that very interesting looking thing, it converges to 0. This whole weird looking thing converges to 0, and but not uniformly. As a result, when we integrate it, then the integral of this series that doesn't go to 0. In fact, if we are to calculate it, the integral of each item, well, first we say the left side, the f of x equal to 0, because the bunch of stuff converges to 0, so this is just 0. Okay, the other side is the integral of each item that's being added up. Each ukx does not go to 0, and you can find that out if you do the actual integration, as I have done here to show you. Okay, now see, we have right here f of x which is 0. Okay, it's identically 0, but it's also defined as this infinite sum. Now, if we consider each individual item here, which is that subtracted by that, and if we were to do the integration, okay, for just one of them, ukx, which by the time you're done, it equals to something like this. And specifically, if you add it all up from the first k equal to 1 to k equal to infinity, then you end up having equal to 1/2, basically. In other words, the sum of all of them does not equal to 1. Or put it this way, specifically, let's see. Now, specifically, the partial sum is equal to nx by the time you work this stuff out. Okay, the partial sum equals to this thing. And this thing, if you are to integrate it, the partial sum is going to be equal to this thing. Okay, and by the time you get through the algebra, it equals to 1/2 minus e to the power minus n. That is, the partial, integrating the partial sum will approach 1/2. And that's, let's see, where did that go? That is also the graph that this is similar to what the graph I showed you last time. Okay, remember what these things look like. These things go to 0, go to the 0 function, but as it goes on, then it just get pushed over here, and the area under the curve, it gets slightly bigger and eventually increasing, eventually and approaches 1/2. Okay, so the area under the curve never decreases, even though the whole each function already eventually approaches. I mean, each point of each function eventually approaches 0. But it goes up first before it goes down, is why this is happening. So there is that's a very interesting situation where you have a bunch of functions, but the integrals are stuck. Okay, in the sense that they each have area underneath, and that area isn't going to 0. If the way you keep pushing it, it just gets squeezed thinner and thinner and rises higher and higher. It just won't go down. And so that is an example where you cannot, just because a series converges to something doesn't mean the integral also converges. So with that in mind, let's look at theorem 13, where in a situation where we have a requirement in such a way that the integral does converge if the original functions converge, and the requirement is that the original the series converges uniformly, and then so let's read theorem 13. UKX are continuous, each one, and that way they're integrable. Okay, and then f of x is the converging uniform is the result of uniform convergence of the series UKX, and then if that is the case, then the integral of f of x is the sum of the integral of each individual function. So that will work if that will work if things are converging uniformly. And so to prove that, we are given epsilon bigger than 0, we will find a large integer m such that for all integers n bigger than m, we have the situation where f of x and the difference between f of x and the partial sum is going to be less than epsilon divided by b over a. Okay, the b over a happens is because of because we're doing integration. Okay, and we're going to so that is stuck in there. And so anyway, this is true because f is a uniformly convergent. I mean, it's a uniformly convergent series. The Sn is, and let's look at the definition again of uniform convergence to refresh our memory what that means. Now, uniform convergence is where f of x and Sn of x is going to be less than epsilon, given epsilon, for all x between a and b. Okay, so like for example, here's my f of x, and there's my Sn of x, and the whole thing is going to be less than epsilon. There is nobody is running up there like the other picture that I just showed you. Okay, Sn of x has to be very obediently following along and not running too far off. And it has to be within epsilon of f of x. Now, given that that is true, then we can this inequality then holds true for all the x's in the from a to b, and this is the critical point of the proof. Okay, once we have this thing down, then we're good to go. Therefore, now being that this is true, then the integral is going to the integral of these two functions would be less than or equal to slapping the absolute value. First, put them under the same integral sign, then slap the absolute value on it, and this thing, of course, this whole thing then can come out to be less than epsilon, being that the integrand is less than epsilon over b minus a. So you can take everything work out neatly to be less than epsilon. That's why this thing is less than epsilon over b minus a, to take care of that. Now, in other words, the difference between the two things the difference between the integral of f and the integral of the partial sum is less than epsilon, then we would rewrite it, which means that as n goes to infinity, the integral of f is equal to the limit as n goes to infinity of the integral of the partial sum, because that is the definition of this relationship. Being less than epsilon means this. Okay. Now that it means this, then from this point we can just rewrite this as n, of course, is sum of ukx from 1 to n, which is, being that this is a finite sum, we can exchange the integral sign with a summation sign, okay, because it's just finite. And so once we would exchange that, then at this point we let n go to infinity. So we got here, and that's exactly what we were trying to prove on top in this line. Now notice that this has to make sense, and this makes sense because f of x is continuous. Therefore, it is integrable. Okay, that matters. Well, just to make sure, okay? Then nobody can say that, but what if f isn't integrable, then what are we talking about? We're not talking, let's not worry about that, okay? Because f is integrable, and I mean f is continuous. The reason it's continuous is because of the theorem we just proved, theorem 12, which states that if you have a bunch of continuous function and it uniformly converges into something, then f is the result is continuous, and that's what we have right here. Okay, and that is ukx is a bunch of continuous functions. F is the result of uniform continuity, and therefore f is continuous as well. And if it's continuous, it's integrable, and nothing weird is going to happen. So then also, of course, we notice specifically that the uniform convergence is the heavy muscle that moved this proof. And what matters, of course, as I have mentioned, is that this part, which applies the uniform convergence, applies for all x. Okay, that's the critical point. That's where it's uniformly convergent. But anyway, if that is the case, then we can stick the integral sign inside the summation symbol if we ever feel like it, which I haven't found the need in the homework. But anyway, but it's there if we need to. And so that is that. Next, let's look at page 305, example A, where we have 1 over 1 plus x. Now that is going to be equal to the infinite sum of minus x to the power k, which converges uniformly from 0 to h as long as h is less than 1. Okay, because that's the geometric series T1. Now, if that is the case, then if we can slap the integral sign on both sides, and like with the theorem 13 that we just had. So if we slap the integral sign on this equation on both sides, then on one side, of course, it becomes this thing right here, which equals log of 1 plus h if you do the integration. And the other side, we slap the integral sign with integrating with respect to x, then we get this thing right here. Okay, and then let's look at example 5 on page 302. And the example 5 says that this particular series converges uniformly from 0 for x going from 0 to 1. Okay, that is, it goes all the way up to 1. And that matters because so we have this series right here on this side, which is the same series. Okay, but this thing is defined only up to where h is less than up to 1, but not including 1. So then here's the rest of the argument, which I wrote out in more detail here. Okay, it's the same thing as what the book says. So what we have so far is 1 plus x, which can be rewritten as this infinite series by the T1 on page 285, where is the geometric series, in other words, which is uniformly convergent for h has to be less than 1. Okay, it doesn't converge. There's no promise about what happens at 1. Now next we have, of course, the slapping the integral sign on both sides. We get this one thing equal to log of 1 plus x calculated. That's log of 1 plus h. and then which on the other side, if we do the integration, then we get this sum. Let's see, yeah, we get the integration, but by the time you get done with the integration, you get this thing right here. Again, this is going to h goes up to 1 but does not include. However, this particular series is uniformly convergent by example E on page 302, is uniformly convergent on all the way up to 1. Okay, and by theorem 12, then f of x is continuous because it's the continuous is continuous from 0 up to 1 of a continuous of a uniformly convergent series. And being that this is uniformly convergent, then f of x is uniformly convergent all the way up to 1. So right now we're just focusing on what happens at 1. Okay, and so being that example E says it's convergent up to 1, whereas before we only say it's convergent up to but not including 1, but example E says it is converges up to and including 1, which means the f of x, which is the sum, is also continuous up to and including 1. And then and in the meantime, log of 1 plus h is continuous all the way up to 1 also, and we have therefore proven that log of 2, okay, we can plug h in as 1 in the equation, which gives us log of 2, which is equal to this sum right here. What is this sum? This is the alternating harmonic series. In other words, this is a third proof that we have done that proves that log of 2 equals to the alternating harmonic series. Next, let's look at subsection 6.3, differentiation. We're still on page 305. We have we're gonna in the previous theorem 13 we did integration. Now we're gonna do differentiation. Well, the differentiation, just like the integration, doesn't always work if you don't have specific conditions. In terms of differentiation, however, even if all the terms belong to C1, okay, the UKX belong to C1, even if the sum, that is the f of x, the sum belongs to C1, that is still might not work. On the other hand, the uniform convergence alone does not ensure the convergence either. I mean the result either, that you can't differentiate on both sides. So uniform convergence alone isn't good enough. Now, so what's good enough? And we'll see that in a minute, that we need the function to be convergent, okay? And then the derivative has to be convergent uniformly. With both those conditions together, then we have a convergent, we can take the derivative on both sides. But that is, we will see that in a minute. In the meantime, we'll see a counter example or something. Example B, okay, where x, the f of x, is going to be equal to x, and that equals to this particular telescopic sum. Now, if you write this stuff out, you need to see the details of this, and please work out this detail yourself. What happens is if you write this series out, it becomes a telescopic, and what you end up with is, remember, f is x. The f of x is just x, okay? This bunch of stuff equals to x. Why? Because if you write it out, you can see it real quick why things are being subtracted, so that you only get, you don't have much left. And so then the partial sum is equals to x minus xn over n. So as n goes to infinity, the partial sum then goes to x. And the difference of the f of x and the partial sum is xn plus 1 over n, and which uniformly convergent to within the range. And we're just only considering from 0 to 1. Okay, so then if you calculate the derivative of this thing, then we get something else, which is this thing, which is also telescopic. But if you look at it very carefully, you notice that for x less than 1, then this thing equals to 1. But if x equals to 1, this thing will be 0. The reason it's 0 is because each term is 0, okay? Each term that you're adding is 0, so the partial sum is 0, so the whole thing becomes 0. So then the derivative does not equal to the derivative of f at 1. It equals in the other places, because the derivative of x is just 1. So it does equal to 1 all the way, but not except the end. At the end, it doesn't equal. So then we have, in other words, we have a problem with that. In other words, the original function has uniform convergence, but the derivative function does not, okay? It doesn't converge uniformly, which means the result of the convergence is not even continuous. And well, as theorem 12 says, if we have a bunch of continuous function that converges uniformly, then the result will be continuous. See, that is theorem 12 that we looked at a little earlier. So which means that this bunch of stuff are continuous, but its result is not continuous, which means it can't be converging uniformly. So next, let's look at theorem 14 on the same page, where we have set up the conditions. As example B shows, when the derivatives don't converge uniformly, then we can't take the derivative equation doesn't work. That is, f prime of x does not equal the sum of the derivatives of the series. And so theorem 14 says if we have a bunch of ukx, which is C1, C1 means is differentiable and its derivative is continuous. Okay, and then f of x is the sum of the ukx. Now the next condition is says that the infinite sum of the derivatives are uniformly continuous. Convergent, uniformly convergent. And if that is the case, so that is then the sum of the infinite derivatives will converge to the derivative of f itself. That is, so we have notice that we have two conditions in theorem 14. Number one, f has to be the convergent result of the bunch of uk. Okay, they better be convergent. You would think that that's obvious, but it might not be. And so first, the ukx had better be convergent. Okay, it doesn't need to be uniformly convergent. It just needs to be convergent at all. And then the u prime kx has to converge uniformly. With both those conditions intact, and of course uk has to belong to C1 to be able to take the derivatives, then we will have our result where we can take the derivative is going to be equal to the sum of the derivative of the parts all added up. Now this conclusion, of course, implies the fact that under those three conditions, the hypothesis, then f prime will be f prime will first exist, okay, and then f prime will also be continuous. That is, well, being that the derivatives are converging uniformly, okay, into f prime, and a bunch of continuous functions converging uniformly is going to result into a continuous function, which means f prime is continuous, which means f is C1. And what I just said is again based on theorem 12. That is, if you have a bunch of uniformly continuous functions in a series, then it will converge to a continuous function. So that is what that is about. And then, and of course, at the endpoints, the derivative just means the one-sided derivative, okay, the left-hand or the right-hand derivatives. And so, having said that, let's set phi of x equals to the sum of the derivatives, or the series, all added up. So that would be phi of x. And let's turn to the next page where we have being the phi of x is the sum of a uniformly continuous function, then by theorem 12 that we just looked at, then phi would be a continuous function. And then, so we can integrate it, okay, it is integrable, and slap the integral sign on one side and slap it on the other side. And by the previous theorem, we can put the integral sign on the inside of this thing, okay, and we're integrating from 0 to h. And so once you slap that in, then by the fundamental theorem of calculus, we will have this side. So that after you do integrate, then it will be ukh, the top limit minus the bottom limit by the fundamental theorem. And so that is and so far so good. Okay, so we have used the integration theorem to prove the differentiation theorem. Now the next part is that being that this f of x is the hypothesis 2 on the previous page, f of x is equal to the sum of ukx, okay, this thing converges, then we can then rewrite these things as these two things here. Okay, we can rewrite it as the first one will be equal to f sum equal to f of h. We can break up the summation sign because being by the definition of the partial sums. Okay, partial sums these are just the limits of partial sums, and partial sums can be broken up if the limits exist, and so we can just break these into the two summations. So this sum will be equal to f of h, and this sum with the summation over here will be equal to f of a. So far so good. And in the meantime, this side is integrating from 0 to h, so we got to that part. And the next step we're going to do is differentiate both sides with respect to x. And if we do that, then we will get phi of h on one side. Okay, and so differentiating this thing with respect to x will give us phi of h, and the other side will give us derivative of f will be let me see, what am I saying? Right, I forgot to say that. Let me say this again. Okay, so if we take the derivative of both sides with respect to h, this side will become f prime of h, of course, which is right here. This side will become phi of h, which is right here, and that thing disappears into 0, okay, because we're taking derivative with respect to h. And what is phi of h? Phi of h is defined on the previous page at the bottom, which phi of h equals the sum of phi of x is the sum of u prime. So phi of h then is the sum of u prime with h in it. Okay, so that is right here, and that is exactly what we were been trying to prove. The f prime equal to, of x equal to the sum of uk prime of x. So that concludes the proof. Now the proof is done with the help of the theorem, the previous theorem, theorem 13. Okay, and it depends on two conditions. First, of course, it depends on the sum of ukx being convergent uniformly into some kind of a phi of x. But secondly, it has where phi of x is continuous. Okay, that's where we got that, is the uniform convergence. It gives us a continuous function, and so with that we are able to integrate, and then we use the fact of condition 2, where f is actually the sum of this stuff, to be able to finish the proof. Now this statement, now notice that people often focus on only that the sum of the derivatives are convergent uniformly, and not pay as much attention to the fact that uk of x itself had better be convergent. I mean, what if they're not convergent? Then your whole story falls apart, okay? Because you're not even dealing with a convergent series, then this is a complete waste of time. And so that is so hypothesis 2 in theorem 14 is just as important as hypothesis 3. And also, understand that hypothesis 3 does not imply hypothesis 2, okay? Just because your pack of u prime of x is convergent does not necessarily mean that this is necessarily convergent. That's because you're taking the derivative. If you if you go back, this stuff is if you take integration, remember this stuff, the u prime of, when you integrate, then it equals the ukx plus any constant, right? Don't forget the constant. And if you stick any constant in here, there's no guarantee that this sum is going to add up to converge at all, right? So that is the reason why hypothesis 3 does not imply hypothesis 2. Now there is one quick example that you can see that the book gives. Consider, for example, ukx equal to 1 plus x to the power k, and then calculate the sum of ukx, then calculate the sum of u prime kx, and you'll find out very quickly that while u prime kx does converge, ukx does not. Okay, and so please do that yourself, as I have done right here. Is a very quick explanation why that is the case. So where is it? Yeah, I think, is that it? UK, no, this one. Okay, right here. All right, so please do that yourself, and we'll move on to the example C. So next, let's look at example C. We have 1 over x, 1 minus x equal to the sum of x to the power k. Okay, that is the geometric series T1. And if we take the derivative of this infinite series, of course, we get the sum of kx, k minus 1. This thing converges uniformly. And now please do that and prove this yourself, as I have done here, to show that it proves uniformly. And especially the book gave us a hint. Okay, let mk equal to this thing, and then prove by you can prove it by the ratio test that this does work. Therefore, it is uniformly convergent by the Weierstrass M test. That is theorem 11. So that is that's that. And then let's see, what is this? And well, okay, so any given number within the range of from -1 to 1, not including the endpoints, can be included inside some closed interval. Then the equation holds for any x from -1 to 1. That is, this when you take the derivative of one side, of course, then you get this one. Okay, and so this equation then holds for any x that is from -1 to 1, not including the endpoints. And you can also type it into Google, and that will, as I did, but I didn't keep a copy of it here. So that the tailored expansion for this thing is exactly that thing. Okay, so we can get the same answer with more than one way, which confirms to us that we're doing the right thing. And so that has we have come to the end of this section. For homework, please do. I have not written it down. Let me do so. All right, so the homework, please do basically, I think all the problems except 12, okay, from 1 to 15 except 12. So that is that. Please go do your homework, and then I will talk about them. I hope this is the right page. Yeah, it is. Now the homework for problem 1 to 8 is just standard stuff, okay, short problems. So I won't talk about them necessarily. This is part of, at the bottom here is part of problem 1. And then the next page for your reference, all the way to problem 8, okay, is I think fairly standard stuff, and then none of them took very long to do, and so but I will just show you for your reference. And then let's see, 6, keep going, and then problem 7 and 8 is here, and so yeah, most of them are quite short, if not, well, all of them are quite short, I think. And so I'm going to start talking about it, talking about problem 9. Problem 9 says that we have some function, and what are we doing? Maybe I should first see what it says. Problem 9 says that we need to show that f is infinitely continuous if f of x equal to that thing. All right, so f of x equals to this thing. We will use the ratio test to show that it is convergent uniformly, and also use the M test, and then we'll take the so one is convergent one way, but in general, the nth derivative that we can show again by ratio test that the nth derivative is also convergent. That is so then we can pull out the mk for the M test. The Weierstrass M test that shows that they are all uniformly convergent, which proves that f is for any derivative. So that's how we prove that f is belong to C infinity. So that is problem 9. Next, problem 10. Problem 10, we're going to do the integration. Let's see. We have. Let me first see what does problem 10 want. So if a function 10, right? If a function we need to show that this function is can be integrated term by term. In other words, it satisfies the integration formula theorem 13, and that is the function is convergent. Okay, if it's convergent, then we can integrate it. And so that is what we do. Okay, it doesn't take much to prove this thing is convergent. It's just x to the power 2k. Once we prove that it is convergent, then we can use theorem. Is uniformly convergent by theorem 11. Then by theorem 13, we can integrate it term by term. And once we've done the integration, the result is this thing right here. And this thing it happens to be the Taylor expansion of arctangent. If you Google the expansion for arctangent, Taylor expansion for the arctangent, you get exactly that. So that is problem 10. And problem 11 is just part of problem 10. It's quite cute. Okay, out of the blue, it wants us to calculate pi over 4. Okay, to calculate pi over 4, then we can just prove this is true. Well, we just stick in, well, what is pi over 4? Pi over 4 is arctangent of 1, right? So, and then arctangent formula, this infinite sum, that it works for x equal to 1, so we're all good. So plug in x equal to 1 in the arctan formula, and that's exactly what the book wants. And that's problem 11. So next, let's look at problem 13, which is a standard proof of epsilon. Okay, you just have to put another g in there, and everything works out very quickly. So that's problem 13. Problem 14, same thing. We have the book wants you to replace b by y, so why don't we do that? And it converges uniformly, of course. It has nothing else to do. Okay, problem 15 is more confusing. Okay, it took me a while to remember what's going on. Is that we're showing, because all the symbols can make you get lost. So to show that u prime converge uniformly does not imply the u themselves converge. And so let's look at f of x equal to u prime. Let f of x equal to u prime, which is uniformly convergent. Then the g will integrate g, okay? So which will be integral of f, which equals to this thing, being by theorem 13, we can integrate on the inside. But then that equals to the sum of uk minus a bunch of constants. See, like I mentioned earlier, that doesn't equal to the uky itself, because unless the constants happen to be all 0 or something, they are not the same thing, which is why you can't just integrate it and call it done, because you're forgetting the good old constant that has to be remembered every single time you integrate something. So so that is why there is a funny situation going on. That's what problem 15 is trying to point out, that hypothesis 3 does not imply hypothesis 2 in theorem 14. Well, because when you take derivative, you don't have to worry about anything, but when you integrate, there's that constant. It's not going away, okay? And you have to think about that. And that will mess up your infinite sum if you have a extra constant for every term infinitely. So that marks the end of this section.